Thanks, Brendan. So I will talk about my new system, GraphG. It's a system which allows you to process very large graphs, but on a very small machine. And it's a joint work with my advisors and the GraphLab team. And although this was admitted to a systems conference, I think this crowd will find it interesting as well as a user of the system. So just to outline, I will first give the basics talk about GraphG, which is my conference talk, a little bit extended, and then I will talk about some new research I've been doing since. So now, recent years, big graphs or networks, analysis of them has become a big topic, and it's because in the last 5 or 10 years we have seen a huge growth of large social networks like Facebook and Twitter. But also in the natural sciences, there has been studies of DNA and found how the genes form a very interesting network and so on. And the analysis of these kind of graphs, there's a huge amount of value inside it, but it has proved to be very challenging. But before we talk about the challenges, let's talk about what can we compute from these big graphs. So maybe a standard example is to look at Twitter. And in the Twitter on the left side, it shows you who to follow, some recommendations. And this is quite normal, quite standard graph algorithm, where the idea is to search for your neighborhood. Who are your friends following? And maybe they would be relevant for you as well. So many similar questions we can learn from graphs. For example, in Amazon or Netflix, if you have seen some movies and the movies your friends have seen, maybe that gives some idea what you would like to see next. But computing on these big graphs has proven to be quite hard. And to cut it short, I think the main problem is that, especially on these natural graphs, like we see in Facebook or social graphs or web graph, they have very highly asymmetric structures. So you have some nodes which have billions of people. For example, in Facebook, Twitter, you have Lady Gaga or Justin Bieber who have millions of followers, but most of us have only few. So that makes decomposing the problem into like equal-sized parts with only a little communication between them really hard. And so building efficient distributed systems for computing graphs has proven to be really hard. So because of that, that no available graph computation system has been really able to tackle these big graphs, people have been forced to use MapReduce or Hadoop, which is definitely not a good fit for graphs, but they haven't had a choice. Now in OSDI 2012, which is next week, our GraphLab team has 2 solutions for this problem. First, we have this next version of GraphLab, which is called PowerGraph, where they show a new solution on distributing the graphs. And the second paper is my work, which talks about disk-based solution, how to actually solve these problems on just a single machine. So can we do that, and why won't we do that? Can't we just use the cloud? In the cloud, you put your credit card in and you get solutions back, right? But from our perspective, who actually write these algorithms for analyzing graphs, it turns to be that writing distributed algorithms is quite hard. It's just a cycle of coding, running it on the cluster, and then debugging, which becomes quite cumbersome on a cluster or in the cloud. So we can visualize common happening if we run stuff on the cluster and something happens. It's really hard to see and debug this problem because the state is distributed and usually the tools for monitoring the processes are quite weak. Instead, what I want to give is that you can run the whole same big problems on just your own machine and use your own IDE to analyze the graphs. It's much easier. And even if you later want to run your stuff on the cloud, this at least gives you a way to develop on your own machine with the real data. Another motivation is quite interesting. So let's assume you have a large number of tasks you want to compute on the same graph or different graphs, but let's say the same graph. For example, in Twitter or Facebook, maybe they want to compute recommendations for different people, and each of those is one task. Now, the current way of doing this is that you actually need a cluster to run these tasks at all on the big graphs, because they cannot fit into memory. But and if you want more performance, you just add machines to your cluster. But there are several problems with this approach. If one node goes down in your cluster, it affects the whole cluster. So you need to deal with fault tolerance and things like that. And usually these systems don't scale very well. So if you add more machines, you don't get the bang for the buck. Instead, with GraphG, this system I'm talking about today, what I want to propose is that because now you can use single machine to solve the same problems. Why just have one machine for each task? And it's so easy to manage, program, and so on. And especially if you double the machines, you get exactly double the performance you need. There are other motivations for this kind of work. Costs, energy consumption, like New York Times just had an article that data centers are humming with a lot of spare capacity, which is just running idle and doing nothing. So if you can do this way, you can use one single machine 100%. And of course, embedded systems and so on. So what is the goal of this research? It's quite simply, I want to use a consumer PC, a normal PC, to solve as big problems as has been solved before with cluster systems, with distributed systems. And I want to do it in reasonable time. And what I mean by reasonable time, of course, I'm not going to be as fast as a 1,000-node cluster, although in some cases it can be faster. What I call reasonable is that if someone has written a paper that they say that this system solves this problem in this time, if I can solve it in this one machine in the same ballpark, I'm quite satisfied. And what I mean by consumer PC, I just mean I have been running it with weaker machines as well, but for these experiments I used the Mac Mini with an SSD. So it's definitely not the cheapest one you can buy, but it's not very big either. So let's talk about the computational model, just as a preface of this work. What kind of programs you can write with this? So first of all, we have a graph with directed edges. And this is quite important terminology. So if we have vertex A and vertex B, and there is edge E from A to B, we say E is A's out edge and B's in edge. And this becomes important soon. For each vertex and edge, we associate a value, which we call associated value. And in this model, both vertex and edge values can be modified. So in many other cases, the edge value is immutable. So for example, it's just an edge weight. But in this case, we allow you to modify it. And then we use the vertex-centric computation model, which I talk next. This is something that recent work like Google Spragle and GraphLab from our university uses. And Google coined the term think like a vertex. So the basic idea is that now when we have this data graph, user defines a function which is run on each of the vertices. And what this function can be, or this update function can do, it can modify the data of the vertex and all its incident edges. And we run this for all vertices in turn or in some other order. Basically the idea is that the function has visibility and it can modify its neighborhood. Then for this work, what are the computational settings? So I assume we don't have enough memory to store the whole graph in RAM. Not even all the values of the vertices. And it might be, in many cases, you may have enough memory to store all the vertices, but for example, in the Yahoo web graph, which is our biggest one, it has 1.4 billion vertices. So if you associate one floating point number for each vertex, you require about 6 GB of memory, which is already quite a lot for a laptop. In addition, we assume that there's enough memory to load one vertex and all its edges into memory. So if you have a vertex that points to all other vertices in the graph, we cannot handle that at this point. But I haven't yet encountered a situation where there would be such a vertex that it wouldn't fit in a couple of gigabytes of memory. Although in the paper, the largest graph was this Yahoo Web graph. Recently, this has been used, even bigger graphs. It has been used on the actual Twitter follower graph. I think it's the August version of it. I cannot unfortunately say how big it is, but I can say that last year it had 15 billion edges, and it's not smaller. So now let's talk about what is the main problem of making disk-based graph computation happen. And it's quite simply random access. So let me talk about it more. Let's assume we store our graph in a file in some kind of adjacency list. So for each vertex, we store its in neighbors and out neighbors, and for each edge, its value. Let's say we update now vertex 5, and it modifies the edge from vertex 19, which is shown in red. Now, when we update vertex 19, we want to observe this edge, change in the edge, so it needs to write the same value in the out edge list of vertex 19. So this would require random write, which is even on an SSD, and especially on a hard drive, really slow. We can, of course, do better. Let's say instead that each vertex owns its out neighbors and has the values of them, but for in neighbors, we just store a pointer where the value is in the out neighbor list of that vertex. So now when we load vertex 5, we need to read the value of the edge from 19 from the out edge list of vertex 19. And this requires a random read, and that's already much better than random write. But still, for sufficient performance, we actually would need millions or hundreds of thousands of accesses per second. And even with an SSD, this is not enough. SSD cannot do anything like that. You maybe can do thousands of, or tens of thousands of random reads. So let's talk about some possible solutions. Maybe we could use SSD as a memory extension. And this was proposed by in a work called SSD alloc in last year NSDI. But like I said, there are just too many edges, and we need to be able to read them, access them millions per second. And this system can do like tens of thousands per second. So it's very efficient, it's a very innovative system, but it's still not enough for this work. Maybe we can compress the graph, compress the structure of the graph so it actually fits into memory, and we don't need to use disk at all. And there is a great work from the University of Milan called a web graph framework, where they are able to compress web graphs to only 4 bits per edge. But in our model, we actually store a value for each edge, which can be a floating point value or something else. And in general, it's hard to compress them, or we cannot say anything about their compressibility. And they are changed all the time, making compression hard. Now, maybe we can cluster the graph. Like social graphs, they have a lot of like local properties. People are connected to people in their home university and their country. Web pages linked to each other in the same company, and so on. But doing this kind of partition, and then we would like to handle each of the graph clusters in memory at a time. But computing this clustering can be expensive, and unfortunately in this natural graph, still the number of edges between clusters is high because people move around, they have friends all over the world, and it's very random. So although this might work in some cases, I think our solution is even simpler and we didn't need it. Then last idea what we could do is that, let's say, we load everything else from disk, but the most important nodes, Lady Gaga's and Justin Bieber's, we hold them in memory. This probably will work in some cases, and I know there is some work on this currently in works. But in general, it gives you unpredictable performance. So maybe it works on some graphs, but not on some others. So let's now talk about what is our solution for this problem. How we can process huge graphs from the disk with very low amount of random access. And this is called parallel sliding windows, PSW. So PSW does the processing one subgraph at a time. So we process one subgraph at a time of the graph until we have finished the graph, and that's one iteration, and then we usually move to the next iteration. For each subgraph, I use this kind of traffic signals here. We load the graph from disk, then we execute the update functions on the subgraph that the user has provided, and then we write the modifications back to disk. Now, let's first talk about how we actually define these subgraphs and how are they loaded. So let's say we have vertices are numbered from 1 to n, and we divide this range of 1 to n to p intervals. And these intervals don't need to be of same, generally they are not of the same size. For each interval, we associate a shard, and shard is a file on the disk which contains all the in edges of these vertices. So it means shard 2 has all the edges that point to vertices in interval number 2, and so on. In addition, we sort the edges inside the shard by their source. So they're sorted by whose out edges they are. Now, let's now load the subgraph for the interval number 1. What we do is that first we load the in edges. They are all in now shard number 1, because that's how we define the shards. And the out edges, because we sorted the edges inside the shards by the source, they're actually in the beginnings of these shards. So we load shard 1 completely into memory, and then these small windows, which are called sliding windows, from each of the shards. Then when we move to the next interval, interval number 2, what we do is we load now shard number 2 completely into memory. Now it has all the in edges that point to interval 2, vertices in interval 2. And now all the out edges for interval 2, they are just next, in each of the shard, just next to the edges for interval 1. So this is the benefit of sorting the edges by the source. Out edges for interval appear just next to the interval edges of the previous interval. So now here you can see an animation how we work a graph with 4 intervals, and on each interval we load one shard into memory, and we have these sliding windows which are going down. And as you see, their length changes all the time, and it's because the graphs are typically quite random in structure. And what is now important, for each interval we need only p large reads. We need to read one shard completely into memory, and then p minus 1 little bit smaller reads. And we do a full pass on the graph, we need to execute p intervals. So in total we have p squared random non-sequential accesses to the disk, which is typically very low. P is usually tens or maximum hundreds. Now the second phase is execute the updates. Now we have loaded this subgraph into memory, and user has given us an update function, and we simply execute the update function on each of the vertices we just loaded. Now what is important to understand here is that we have these edges which have data as set values. They are actually stored as pointers to the blocks we just loaded from the disk. So if we have neighboring vertices loaded into memory, their edge objects will point to the same value, point to the same address in memory. And these are big blocks loaded from disk. And now it will make easy for us then to write this back to the disk. And one important point to understand here is that changes to the edges are immediately visible. So if a vertex changes its neighboring edge, its neighbor, when it will be updated, will observe this change immediately. So we call this asynchronous computation in opposition to the bulk synchronous way, which is standard in distributed systems. So like I said, in the last third phase, we write these modifications to disk, and because the changes were done in the disk blocks, we just write them back where they were loaded. Again, we just need p large writes. They are similar to the reads, or same as the reads for each interval, and p squared per iteration. And writes made in interval 2 are immediately visible for when we load interval 3. So again, we are asynchronous. Let me actually skip this. This just formalizes a bit what we mean by asynchronous. Some additional details. Now I was talking only how we load edges, but actually we also associate value for each vertex. And this is quite simple because we actually handle the vertices in order. So we just store them in a flat file. In addition, this supports selective scheduling, so we have a big vector saying that should each vector be updated or not. And this way you can do dynamic applications, which only update the parts of the graph which actually need updates. A little bit about the I/O complexity. In the paper, we have a theoretical analysis in the Agarwal-Witters I/O model, but the basic intuition is here that if an edge is between vertices in the same interval, it needs to be loaded only once per iteration from disk. But if it spans intervals, then it will need to be loaded twice. So in worst case, we have only 2 times more I/O than in the best case. So there's not really much motivation to actually try to, for example, optimize your graph to order your vertices so that the nearby vertices would have same close-by IDs. So in summary, we divided the vertices to p intervals. We load a subgraph at a time, load, compute, and write the interval. And this requires only p squared random accesses per iteration. And this means PSW works both on SSDs and hard drives. It's about twice as slow, or half as fast on hard drive than it's on SSD. But it's very useful. Okay, I think I had the same slide twice. Okay, let's talk about the implementation quickly and some experiments we made on the system. So GraphG is the system, name of the system, and its implementation of the algorithm I just described. There are several optimizations to make it run faster and save memory, but you can see the paper for those. In addition, it includes a program which can create these shards, and it doesn't require much memory either. It's done in C++, but there is also a Java implementation available, and it's open source, of course. And I have really tried to focus on the ease of use, so there's not much dependencies, it's headers only, so it's really easy to use. So let's start the evaluation. First thing I want to evaluate that is this system any good? Can you use it for anything? Maybe as a researcher I should not ask these kind of questions. But it's a little bit hard to analyze whether it's usable or not, but here's a list of all the algorithms that have been implemented on it. So basically, almost all the algorithms you can implement on GraphLab or Pregal, you can do with this. And usually you get good enough performance. So for example, things on the left side I talk in the paper, but since the paper there has been, Danny Bixson has implemented several collaborative filtering algorithms which allow you to do very big matrix factorizations on this. Then if we agree that you can use it for something, now the next question is that is it actually fast enough? So our setting for the experiments was, most of the experiments were done with this Mac Mini, with 8 gigabytes of RAM, an SSD, and a dual-core processor. And here is the list of the graphs we used for the experiments. These are the same graphs that are used by most graph framework papers. So the biggest one is Yahoo Web with 6.6 billion edges, and then we have several others which have billions of edges. So they are pretty big. And you can see the P is quite low. It's about 50 usually, so the number of shards. And so our goal was to solve as big problems as reported for distributed systems in a reasonable time. And so let's see some examples. In the papers, there are more, and you can see the citations for all of these results. So PageRank, Spark is a new system from Berkeley. By using 50 machines, it's about twice as fast as GraphG. WebGraph belief propagation, which work from CMU UConn, using Pegasus, which is a Hadoop-based system. GraphG is a little bit slower than Pegasus is on 100 machines. For matrix factorization, we raced against earlier version of GraphLab, and which is an in-memory system, and it's about twice as fast as GraphG, but still we are in the same ballpark. Triangle counting is something that we have had a talk in ML Lunch as well, and there was a paper in DubDubDub, I think 2011, where they use a Hadoop cluster of 1,636 machines to compute triangles for each vertex in the Twitter graph. It took about 450 minutes or so, and with GraphG it's about 1 hour. So I think as a conclusion, I dare to say that GraphG can solve problems in reasonable time. And what is even more important, it can handle the same problems that has been done on large systems before. Now, I just mentioned that our group has another paper in OSDI, which is called PowerGraph, or the other name is actually GraphLab 2. And it's way faster than anything before. But still, if we compare it to GraphG, with 64 more machines, it can do PageRank about 40 times faster than GraphG, and triangle counting about 30 times faster than GraphG. So now, if you really want something that's really fast, definitely you need to use GraphLab. But still, the relative performance of the amount of computation per CPU is pretty good in GraphG. Let's evaluate the system a bit inside. So first thing we want to analyze is that how well does it actually scale to big problems? So here on the x-axis, we have the graph size, which is defined as the number of edges the graph has. And these dots are different experiments we made. And on the y-axis, we have the throughput, which is kind of how fast it computes, so how many edges it passes per second. And the red line is an least squares fit to this data. And we can see that the relative performance is almost constant when the graph size grows. There is some variation because of the because there are some structural differences with the graphs, which can cause like up to 2-time difference. But still, the running time is roughly linear with the graph size. On a hard drive, this is on SSD, on a hard drive, the numbers are about twice. So let's analyze the bottlenecks. GraphG is actually parallel, so you can use many threads to do the computation and also loading of the graph from disk. But because already almost on one CPU, it can saturate the I/O bus, so it's really bounded by the performance of the disk. We don't get much benefit on algorithms which have very low computational complexity, like connected components of PageRank. But if we look at triangle counting of matrix factorization, where there's actually a lot of computation happening, then we can get reasonable benefit from using more threads. In addition, what you can do is that you split the shards to many drives. So then you can parallelize the disk I/O and get this done on a hard drive, not SSD, and you can get some benefit from that as well. So a summary of the experiments, it seems to be able to solve as big problems as existing systems and very reasonable time. And it's bottlenecked by the disk I/O bandwidth and memory bandwidth. So we can hope it will get faster and faster when SSDs get faster and so on. OK, so one more thing. Let's talk about graphs which change over time. So these were for graphs which are static. So we are not adding or removing anything from the graphs. But in most cases, like Twitter or Facebook, the social networks, they are growing every second. You get more edges. So every second, people make friends. They unfriend some as well. And what would we like this kind of system to do is that we don't want to compute always from scratch when we get new edges to the graph. Instead, we want it to be computing all the time. And when new edges are added to the graph, to adapt and compute only based on what is new in the graph. So how can we do it is in the PSW model. It's actually surprisingly simple. So if you recall, we have these shards. So for each shard and interval pair, we defined something we call an edge buffer, which is an in-memory buffer which stores the new edges which come from some process, for example, from Twitter Firehose. And so when we load an interval, some interval, in addition for looking for edges from the shards, we also look at these edge buffers. So now what happens when there are too many edges in the memory? What we do is we take such shards which have a lot of new edges into them and write them on the disk. We recreate the shards on the disk. And if they become too big to fit in memory, we can split them into two. And at the same point, when we rewrite the shards, we can also remove edges that were deleted, like permanently. So let's evaluate this. To evaluate this, we made a quite simple streaming graph experiment. So we started with a subset of the Twitter graph, or older Twitter graph. And then from hard drive, we loaded either 100,000 or 200,000 edges per second and inserted them into the graph, while at the same time running PageRank. So you could think about, like Twitter could do something like this, to keep the list of the most influential users updated all the time. I have to say this 100K and 200K edges per second, it's quite a high rate. I think in Twitter, probably the real rate of adding followers is some hundreds of edges per second. So let's look at the ingest rate. So can we actually keep on adding 100,000 or 100K edges per second? And so the red line shows what is the actual rate of edges inserted into the graph when we had this target of 200K per second. And the black one is for the case where we had a target of 100K edges per second. And you can see that the system can sustain the rate of 100K edges per second roughly until the end, until we run out of edges, actually. And why there is some variation is that when the graph gets bigger, also like splitting the shards and rewriting them on disk becomes more expensive. But 200K it's too fast, right? What about the computation? I said we were computing PageRank at the same time we were adding edges to the graph. So if the blue line is the computational throughput on a fixed graph doesn't change, we can reach about 30 to 50% of that rate. So in practice,